Hello, everyone. Thanks for taking time to attend this tutorial on Lyapunov drift arguments. So this is a three-part tutorial. This is jointly conducted with my student Zaive Chen, and I'm Sivateja Magaluri from Georgia Tech. In the first part, I'll talk about introduction to stochastic recursions and overview of drift arguments. And in second part, Zaive will talk about reinforcement learning. And in third part, I'll come back and I'll talk about stochastic processing networks. So this tutorial includes joint work with several of my co-authors. This is work that has been happening in my group for many years now. This includes co-authors like Shrikant, Sanjay, and Karthik, and many students in my group, as well as students outside my group that have collaborated with me over years. So let's start with the first part of this tutorial on introduction and overview. So the topic of this tutorial is on stochastic recursion. So we all know what a recursion is. Xk plus 1 is some function of xk, and this function can depend on time. So here we are interested in stochastic recursion. So this recursion also has some noise in it, a random variable in it. And this W case can be either an IID sequence of random variables. They can be martingale differences. They can be Markov chains. So one can imagine all kinds of general settings. And why are we interested in this? Because in the next few slides, I'll motivate the study of stochastic recursions using various examples. And we are interested in many questions that arise in this context. One question is, what happens if I run this recursion for a very, very long time? K goes to infinity. Is there a steady state? What is the behavior of the steady state? Another type of question we may be interested in is, what happens? I want to run it for quite a while, but not let K go to infinity. So if K is a finite number, but let's say large enough, then what is the behavior of this recursion? So this is a very, very general setup. In this talk, we'll focus on a slightly more specific form. The first thing I did is I wrote this in the form of xk plus something. That is without loss of generality because I can add and subtract xk. But the second thing which is with loss of generality is that I made this capital F not depend on time. It's a fixed function, and alpha k is a step size. So I took the time dependence of little f and then put it in the step size alpha k. So alpha k is typically called the step size. Cool. So in the next few slides, I'm going to show you at least two very different settings where the stochastic recursions occur. So the first one is I want to solve fixed point equations. This is very similar to solving roots of a function, except that here I don't have a function, I have an operator. X. So in this talk, X is going to be an n-dimensional vector, so it's an Rn. And H is an operator. All it means is that it takes a Rn vector and spits out an Rn vector. And I want to solve a fixed point of H, which is I want to solve H of x equal to x.
Excuse me, one question,
Yes.
Yes. When you said there is no dependency of time in capital F, you mean that WK does not include a time?
No, WK can be a Markov chain, but it cannot be time inhomogeneous, for example.
Okay.
Or it can be IID, in which case there's no time dependence.
Okay.
I mean, xk itself depends on time, but this functional form does not depend on time.
Yeah, because if you include time in WK, then you can generalize it again back to.
Right. So I haven't precisely told you the assumptions. Typically, we work with IID or martingale difference or homogeneous Markov chains. Then there's no time dependence. So why are we interested in solving fixed point equations? Zaive will talk about MDPs and reinforcement learning in part 2 of this tutorial. And the Bellman equation plays an important role in reinforcement learning. And Bellman equation is of this form. So solving Bellman equation is like solving a fixed point equation. And I haven't told you much about what H is. In general, it can be nonlinear. Many a time it is indeed nonlinear. But suppose it is linear, then solving for this fixed point equation is same as solving linear set of equations. So the canonical form of a linear system of equations is ax plus b, x equal to b. And if I define my H to be a linear operator of this form, a plus I times x minus b, I is an identity matrix, then solving hx equal to x is same as this because you can cancel x on both sides. There are many ways of solving a linear system of equations. We'll talk about one particular method in the next slide. And the third example of solving fixed point equations is in optimization. So if I define suppose H is some nice enough function. What do I mean by nice? I'm not being very precise, but let's say convex for the time being. convex and some other nice properties. Then if I define my capital H, so H is a function, so it takes a vector spits out a scalar. If I take its gradient, I get an operator because gradient is always a vector. And then if I define my H to be of this form, minus some constant times the gradient plus X, then if I think of Hx equal to X, that's same as solving gradient of little h equal to 0, which is same as finding the minimum of this function little h. So optimization also fits into this fixed point equation. So this third example may look like it is contrived, but actually there are many other ways one can actually do all of optimization theory in terms of solving fixed point equations of operators and finding roots of operators in general using something called monotone operators, but we'll not get into it. So I think it's enough if we understand that optimization also fits into this framework. OK, good. So now how do we find this fixed point? So a simple idea is to start from somewhere. X0 is some initial state, initial vector, and then keep repeatedly applying this operator h again and again. Xk plus 1 equal to h of xk. So the question is, does this work? And the answer is yes, if the h satisfies something called a contraction property. What's a contraction property? Take two vectors x and y. They have some distance between them. They're in a vector space Rn. And if I apply h to them, I'll get two new vectors, and the distance between them has decreased. So it's decreased by a factor gamma. Gamma is, sorry, it should be beta. I'm going to use beta in the next few slides. So the contraction factor beta should be strictly less than 1. And suppose this is true, then there is a unique fixed point, x star, and this iteration converges to the unique fixed point geometrically fast. In optimization, this is called linear convergence. OK, very good. This is very nice. But the problem we are going to be interested in is stochastic recursion. So we need some noise. There is no noise here, right? Everything is deterministic. So in order to implement this iteration, I need to have access to this h. I need to calculate h on any vector. Suppose I don't know h, but I have an access to an oracle. What does this oracle do? I give it x. Its job is to give me h of x, but it's not too good at its job. So it ends up giving me a noisy version of h. It gives me h of x plus w. W is a noise. Again, this can be IID or martingale or Markov chain and so on. And then what happens? Then can we now, even in presence of the noise, can we do this iteration? Will it converge to the fixed point? And the answer is kind of yes. And this is what is stochastic approximation. So instead of using this simple iteration, we'll look at a slightly more complicated iteration, which was proposed by Robinson Monroe in the 1950s. What this is saying is that in the simple iteration, I'm at k. At time k, I'm at xk. At time k plus 1, I should go to h of xk plus wk. But instead of going all the way there, I will kind of take a linear combination of my current xk and the one that I'm supposed to go. Why? Because there is this noise. I don't trust this oracle too much. I have to go from xk to the h of xk, but since I don't trust it too much, I don't go all the way. I go to some point in between. And what point in between? It's determined by this alpha k. This is the wake vector. And in general, I'm instead of keeping it constant, I'm making it time varying so that I have more flexibility. Maybe as time after a lot of time, maybe I'm quite confident about being close to fixed point. Then maybe I want to make this alpha k small so that this noise doesn't disrupt things too much. OK, so this same update can be written in this form as xk plus 1 equal to xk plus alpha k times h of x plus w minus x. And this alpha k is typically called the step size. And I started off the talk by showing you a stochastic recursion. So this is essentially of this form. My f is basically this h of x plus w minus x. And typically one assumes, like I've been saying, that this w is either IID or martingale difference. Whatever it is, it's mean 0 on bounded variance. I'll talk more about bounded variance when I get to stating some theorems on this. OK, let's now go back and look at the examples that we've been talking about. So to solve this fixed point equation, I want to use this stochastic approximation. This is the first example of a stochastic recursion. And I told you that this arises in many places. So to solve the Bellman equation in reinforcement learning, when we use a stochastic approximation of this form, we get various reinforcement learning algorithms like TD learning, Q learning, and so on. And like I mentioned, Zaibe will talk more about this in part 2. And we talked about linear equations where h is of this form. So if I take this h and put it in the stochastic approximation, I get a linear stochastic approximation that looks like this. And I mentioned how there are many methods to solve linear system of equations, but we can use this method if we don't have access to A and B, but we have only noisy Oracle access. And finally, I mentioned about optimization, where h has this form. So if I take this h and put it in this stochastic approximation, I get an update that looks like this. I dropped the eta, I kind of absorbed it into alpha k. And then wk is mean 0, so I'm not worrying too much about the sign in front of it. So now this is the famous stochastic gradient descent, which lies at the heart of machine learning. So various supervised learning algorithms, for example, lasso, logistic regression, and so on, have SGD at their heart. So okay, this provides enough motivation for stochastic approximation, which is a special case of stochastic recursion. Let me show you one other example of stochastic recursion that comes from a completely different domain, queuing theory. So queues are in general studied either in discrete time or continuous time. For the purpose of this tutorial, we'll work only with discrete time queues. So there's a server and there's a buffer for customers to wait until their service. Customers arrive according to some process. They wait until they're served. Once they're served, they leave the system, they depart. And time is slotted. In each time, the number of customers that show up is an IID random variable, and I denote it by A of k. It has mean lambda and variance sigma A square. In each time, the number of customers that the server can potentially serve is also an IID sequence of random variable. And then I call it S of k, and it has mean mu and variance sigma S square. And I call this potential service as opposed to service because suppose there are no customers, and then the server could have served 3 customers in the time slot. But in reality, it doesn't serve anybody. It's just sitting idly because there's no customers. That's why S is called the potential service. And the total number of customers in the queue is Q of k, the queue length. So the queue length simply evolves as follows. If I have a queue length of qk at the current time, and I want to find the queue length at the next time, all I have to do is add the new arrivals, subtract the service. But remember, this is only potential service. I have the service only if there are customers to take that service, which means the queue length will never go to 0. Will never go negative. Sorry, negative queue length does not make any sense. So what I do is I do this bracket plus. Bracket plus is just defined as max of whatever is inside it with 0, which means if the inside thing is positive, it doesn't do anything. If the inside thing is negative, the output of this bracket plus is just 0. I can write the same thing in this form. Why? This qk can be sent inside the max. Then this is just saying max of 0, q plus a minus s, which is essentially the definition of the bracket plus. OK, why did I write it in this form? Because this exactly looks like our stochastic recursion. Instead of x, I have a q. Normally in stochastic recursion, it's a vector, but here we have a scalar because I'm working with single server queue. In part 3 of this tutorial, I'll talk about more general stochastic processing networks where I have multiple queues. So there we'll work with vector of queues. And the step size is 1. There's no step size. So it's simply a 1. And this f here is a nonlinear function that involves this max, which is again coming because of this bracket plus. And in some sense, this simple nonlinearity is at the heart of all of queuing theory. So if you didn't have this nonlinearity, this is just a linear recursion. It's much simpler to analyze. And all of queuing theory is about dealing with this nonlinearity of bracket plus or max, however you think about it. And it's related to what is called as Corovert map in queuing theory and so on. OK, and what is the noise? So here arrivals and servers are random, and they basically form the wk. A minus s is the w, and like I mentioned, we assume it is IID sequence of random variables. OK, so with that motivation for stochastic recursions, let me present the outline of this tutorial. Like I mentioned this in 3 parts. In the first part, I'll start. I already gave an introduction to stochastic recursions. In the remaining time in the first part, I'm going to present the key ingredients of our method, the Lyapunov arguments. I'll first give an overview of various Lyapunov arguments, and then I'll show how these can be used to study a single server queue and a very simple stochastic approximation. And so the purpose of the first part is to give an overview of the kind of arguments that we present, but the results themselves are not too spectacular. These are quite well-known results, like over the last several decades. But by the end of first part, you should be able to see the connection between various stochastic recursions and how to think of them in terms of ODEs and what are the main ingredients of various proofs. Then in the remaining two parts, we'll focus on each of these applications. For example, in part 2, we'll focus on stochastic approximation with its use in reinforcement learning. And a simple stochastic approximation result that I'm going to present in the first part is not going to cut it. We need to look at more general stochastic approximation. And to do that, we'll face a challenge, and we need to overcome that by constructing a novel Lyapunov function. And Zaiwei will talk about this. And finally, in part 3, we'll come back to queuing. And then I'll talk about a very general stochastic processing network. In particular, I'll focus on what is called as an input queued switch, which can be used to study data center networks. And in particular, this has multiple queues. In part 1, I'm only going to focus on single server queue. When you go from single queue to multiple queues, again, there are going to be challenges, and one needs to overcome them. And I'm going to show how to overcome them and what novel Lyapunov functions will get there. So before going forward about Lyapunov drift arguments, I want to first talk very, very briefly about classical methods that have been used to study stochastic recursions. So this is our stochastic recursion. I rewrote it. I sent this xk onto the left, alpha k onto the left. I get something like this. Now I squint my eyes, wave my hands, and then say that this left-hand side kind of looks like a derivative. If this alpha k is small, blah, 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 then this can be thought of as x dot. Then on the right-hand side, there is noise, but then if we're doing something like this, maybe this noise vanishes, or I wish the noise vanishes, then I get an ODE of this form. X dot is equal to f of x. Okay, I made it look as if this is like some vague connection I'm trying to make intuitively, but actually this connection can be made very, very formal by scaling time and magnitude appropriately and taking appropriate limits. And then one shows a process level convergence of this stochastic recursion to this ODE. And then studying this ODE will give us results on the stochastic recursion. And this approach has been taken in both the domains, in both queuing and stochastic approximation literature. In queuing literature, this is called fluid limits, which was started by Jim Dye in his breakthrough paper in mid-90s. And the punchline there is that if you look at an ODE that corresponds to a queuing system, and then if the initial condition of this ODE is some positive value, and suppose you can show that no matter what positive value it starts with, there is some t after which the ODE is 0. X becomes 0, then the queuing system is stable. This is a big theorem from fluid limit approach. On the stochastic approximation side, one has a very similar theorem. The theorem says that for the stochastic approximation update, look at the corresponding ODE, and suppose this ODE is globally asymptotic stable. What does that mean? No matter where you start, this ODE converges to its x star, its fixed point x star. Then the original stochastic approximation also converges under appropriate choice of step sizes also. So, and this was work that also happened in the 80s and 90s, and it culminated in a book by Borker in 2009. But to actually show this formally, one uses heavyweight machinery to show established process level convergence and so on. And but in contrast, we'll directly work with the stochastic approximation, and we'll use Lyapunov drift arguments, and our arguments are going to be much simpler. A key limitation of the ODE approach is that it only gives us asymptotic behavior. What happens is k goes to infinity. But if we want to understand more refined behavior, for example, in the queuing context, this corresponds to not just stability, but some handle on what the queue length or the delay is. Then one can think of the ODE scaling as law of large number scaling. One can then look at central limit theorem kind of scaling, and then get a stochastic differential equation. These are called as diffusion scaling, diffusion limits, and Brownian motion processes in the limit, like a reflexive Brownian motion process. And there is a huge theory of heavy traffic study of queues using the SDE approximation. However, like I mentioned, this gets even more intricate. One uses a lot of technical machinery in this, even when compared to ODEs. And there are certain steps in this approach that are very challenging. And in many papers, these steps are not done, especially there is an interchange of limit step, which gets very tricky. There's also some work on getting finite sample bounds for stochastic approximation, not just asymptotic, based on bounding the errors with respect to ODE, but it is fairly limited and there are only very few results. And like I mentioned, our approach has no scaling, no law of large numbers, no central limit theorem scaling, no process level convergence. We directly work with the original stochastic approximation and then use Lyapunov arguments to study it. So in that sense, this is much, much simpler. One doesn't need to have like background on Brownian motion and so on to use these methods. But the challenge in using Lyapunov drift arguments is constructing the right Lyapunov function. And in part one, the Lyapunov functions I'm going to use are going to be very simple. But in the remaining two parts, we'll show how to generalize, we'll provide rules of thumb on picking these Lyapunov functions in various applications. And it turns out that in spite of its simplicity, the Lyapunov approach is very, very powerful. And we'll show in part 2 and part 3 how it can be used to, it was used to solve various open problems. Okay, so in this slide, I'm going to present an overview of various Lyapunov arguments that we are going to use in this tutorial. We are only going to work with stochastic recursions. So we'll only work with the arguments that I'll present in this column, but I'm also showing you the corresponding ODEs because in our approach, we don't care about ODEs. If you look at a typical proof based on this Lyapunov drift approach, there are no ODEs in the proof, in the paper. But we use ODEs to develop intuition. We use ODEs to construct Lyapunov functions. So that's the reason I also want to show the ODEs for each of these Lyapunov arguments. And the general stochastic recursion we have is of this form: xk plus 1 equal to xk plus step size times f. And v is a Lyapunov function. For some of the results I'm going to state, v needs to be non-negative. For some, that's not required. And the drift of this Lyapunov function is defined as follows. Suppose I start in state x, and then I look at the future state xk plus 1, which is going to be random. And then I take its expectation and look at the difference. This is called the drift of the Lyapunov function v at state x. And the ODE that corresponds to the stochastic recursion, as I mentioned in the previous slide, is this x dot equal to f of x. And instead of drift in continuous time for the ODE, we'll look at the derivative of v. So v is a function of x, but since x is a function of time, I can think of v as a function of time. With abuse of notation, I'm writing v dot, which means dv by dt. And using chain rule of differentiation, this is just gradient of v dot product with f of x. This dot product is the standard Euclidean dot product. So the first kind of Lyapunov argument we'll see comes from what is called as global asymptotic stability in dynamical systems literature, which says that if I can show that my v dot is strictly less than 0 as long as x is not equal to x star. X star is where I want to converge. This is saying that as long as I'm not at x star, I converge, my v strictly decreases, then x should converge to x star. When we look at the stochastic recursion, the generalization we have looks like this. So suppose xk is a DTMC, discrete time Markov chain. Time is discrete. I'm also assuming that the state is discrete. And then I look at the drift. So the drift should be negative, very similar to what we have here. But I'm relaxing it a little bit. The drift should be negative only outside a finite set. Inside the finite set, it can be positive, but it has to be bounded. Then I don't quite have convergence like in the ODE setting because of the noise that is kind of trying to drive me all around, but I'll have positive recurrence, which means a steady state exists. So this is called Forster-Lyapunov theorem. So these kind of arguments are essentially establishing stability or ergodicity. This is the first and simplest kind of Lyapunov argument. The second argument says the following. So instead of just saying that v dot is negative, have a slightly more stronger understanding of it. V dot can actually be bounded by minus f. F is a non-negative function again. So if we have something like this for the ODE, then we can essentially integrate on both sides and then show that integral of f of xt is bounded by v at time capital T minus v minus the initial v. And since v is positive, I can further get rid of this v of 0. And then if this will enable me to bound f of xt. For example, if I look at the min of all these f's from time 0 to capital T, the decays as 1 over t. If v of xt is bounded, for example. So I'll not talk much more about this, but arguments like this are used in optimization to show rates of convergence, especially rates of convergence that are of the form 1 over t. As opposed to this, we'll look at the stochastic variant of this, which has slightly different flavor. Here, again, I look at the drift, and instead of just saying it is minus epsilon, I actually say it is minus f of x plus g of x. In fact, this Foster-Lyapunov can be thought of as a special case of this. Then, in steady state, under some conditions, I'm not being very precise about the theorems I'm stating in the slide. This is just to provide an overview. So under some conditions, one can show that in steady state, the expectation of f is upper bounded by expectation of g. Many times when we use this, g is actually a constant and f is a quantity we need to bound. So we essentially have a steady state bound on expectation of f of x. So one way of thinking about this is take this inequality, take expectation with respect to steady state on both sides. So if you take the drift and take expectation on with respect to steady state distribution, then what you have is expectation of v of xk plus 1, which should be the same as expectation of v of xk. So this drift in steady state should be 0. And that's essentially what we are getting here. Even though this is as simple as setting drift to 0, there is one small intricacy that I'll not mention at this point. I'll talk about it later. So this is the second kind of argument that we'll use. Simply setting the steady state drift of some function to 0. And if we can bound the drift of that function by some f, we can get a bound on f in steady state for the stochastic recursion or in transients for the ODE. And recall that in the previous case in stability, these two theorems are the counterparts, the ODE and stochastic recursion. But here these two theorems are slightly different. Here, the first theorem is talking about transients. The second one is talking about steady state. And I'll leave it like that because we are not going to use the ODE thing in the second case. We'll only use the setting drift to 0. And finally, the third one is in some sense the strongest. Suppose I can show that this v dot is not only less than 0, is not only bounded by negative of some arbitrary function, but it's actually bounded by negative of itself. V dot less than or equal to minus some constant times v. Then one can show that it can be bounded by this exponentially decaying function. So suppose this was an equality, then it is very easy to see that the ODE has the solution v t equal to v0 e power minus eta t. And using Grunwald's lemma, one can show that even with inequality, this is true. And this is called global exponential stability because this is basically saying that you converge to the fixed point exponentially fast. And the stochastic variant of it is essentially the same. My drift is bounded by minus eta v. Then I can take the definition of the drift, take expectation on both sides, and then I essentially get expectation of v xk plus 1 is 1 minus eta times expectation of v xk. And if I solve this recursion, I get geometric convergence. This is geometric ergodicity. We'll use all three, but when we use the third one, we'll use a variant of it. Instead of geometric rate, we'll see that we'll have a slightly different rate. Okay. Now I'll change gears, and in the rest of part 1, I'm going to show you how to use these arguments first in the case of a single server queue, and then to study stochastic approximation. So let's start with a single server queue. I already introduced the model. I introduced the bracket plus notation, but a convenient way of analyzing this bracket plus is to introduce something called unused service, which basically keeps track of the case when there is potential service, but there are no customers to use the service. And the key observation about this unused service is that qk plus 1 multiplied by uk is 0. Why? Suppose uk is 0. Suppose there are a lot of customers, there's no wasted service. Then the product is clearly 0. 0 multiplied by anything is 0. Suppose uk was non-zero. Why do you have unused service? You have unused service because there were no customers to serve, which means the queue was empty, which means qk plus 1 is empty. So whenever uk is greater than 0, qk plus 1 is equal to 0. That's why you have this product. So in fact, one can think of this uk as capturing whatever information is in the Skorohod map and so on. So one can think of all of queuing theory as essentially a way of understanding this uk. OK, and so we have lambda and mu. We'll use epsilon to denote mu minus lambda. So suppose lambda is less than mu, that is epsilon is greater than 0, then the Q is stable. By stable, I mean it's positive recurrence. And to show this, all you have to do is use Forster-Lyapunov theorem using Q square as a Lyapunov function. So look at the drift of Q, and then it's basically Qk plus 1 square minus Qk square. Substitute for Qk plus 1 using this. Expand the whole thing using binomial theorem. Kill a bunch of terms using the property of unused service. And essentially, after some simple manipulation, one can show that this is less than or equal to minus 2 epsilon times Q plus a constant, the second moments of arrival minus service. And if Q is large enough, then the negative term dominates and the whole thing will be negative. So this fits into the Forster-Lyapunov theorem. I'm not showing you what the finite set is, but it is very simple to define. It should just be large enough so that this negative term kills the positive term. If you increase Q, the negative term becomes larger, but the positive term is not affected. So then using Forster-Lyapunov theorem, we have stability. The only thing I need is that this epsilon, which is mu minus lambda, should be positive. Okay, so this is this is a very simple argument. This is fairly well known. I think Sigmatrix audience have seen this multiple times. The next thing I'm going to talk about is to get a handle on the Q-lengths. And I'll do this in heavy traffic limit. That is when epsilon becomes very small. So this was first done by Kingman in the 1960s. And here all I do is I take, so in the previous slide, I used the first Lyapunov argument, the Forster-Lyapunov argument. In this slide, I'm going to use the second one, which is setting drift of a function to 0. So again, I take the same quadratic function and then set its drift to 0. And whenever you set a drift of some function to 0 in steady state, you need to make sure that this expectation in steady state is finite. Otherwise, we are doing infinity equal to infinity, and we can prove any nonsensical result using that. So, but in this talk, I'm not going to show how we prove that. But you just have to be aware that that's an additional step that needs to be done. And once you have that, then you can set the drift to 0. Then we essentially repeat the same calculation as before. Qk plus 1 is substituted using the update, expand using binomial theorem, kill some of the terms, rearrange the terms. Then we get something like this. So first thing to notice is that there is a mu minus lambda, which is epsilon in the denominator, which means if epsilon is very small, this is blowing up. This is going to infinity. So in heavy traffic, the Q lengths blow up. That is the first observation. And this is an equality, no inequality anywhere so far. And the second thing is there's a epsilon in the denominator here also, but then one can show that the numerator is at least order epsilon, which means this whole thing is basically like a constant. It's negligible in, compared to the first thing. So I want to understand what happens to the Q length in the heavy traffic limit, and but then it blows up as 1 over epsilon. So we look at epsilon, we multiply by epsilon on both sides, then take the limit. The second term vanishes, and all we have is the first term, the 2 in the denominator. And this, I have the second moment. Second moment can be written as variance plus mean square, but the mean will be order epsilon square, so it gets killed. So essentially, we have that the heavy traffic scaled, that is epsilon multiplied Q length in the mean Q length in the limit as epsilon goes to 0 converges to simply the average of the variances. An interesting thing to notice about this is that it doesn't depend on the whole distribution. The distribution of the arrival process and service process can be arbitrary. As long as the means and variances exist, we have a result that looks like this. So in the previous slide, we talked about what happens to the limiting mean Q length. But suppose I'm interested in the whole distribution of Q length, not just the mean. Then we can use the MGF method. This was developed in work jointly with my student a couple of years ago. And the idea is to repeat essentially the same thing as before, but use an exponential test function instead of a quadratic test function. OK, very good. Now I'll substitute Qk plus 1 using the update. But then earlier when I had Qk plus 1 square, I simply used binomial theorem to expand it. Now I have exponential and I have all these terms in the exponent. There's no binomial theorem for exponential. There's binomial theorem for any power, but there's no binomial theorem for exponential. So what we need a new trick here. So the trick that we use is basically this relation. E power theta epsilon is not important. Qk plus 1 minus 1 times e power minus uk minus 1 is 0. Why is this true? This is actually very, very simple. Notice that the function e power x minus 1 is 0 if and only if x is 0. So suppose u is 0, and then this term will be 0. So the product is 0. Suppose u is not 0, then this is saying that qk plus 1 must be 0. So suppose u is non-zero, then qk plus 1 is 0. So the first term should be 0. Therefore, this product is 0. So essentially, this lemma is just a rewriting of the relation qk plus 1 times uk equal to 0. So remember, I mentioned how understanding unused service is at the heart of queuing theory. So when you want to go understand the steady state distribution, the heavy traffic limiting distribution of queue length, then you have to generalize this relation. And then this way of generalizing is very powerful. OK, so once I have this lemma, then I can expand this out. I can multiply these two terms and qk, and then I'll get qk plus 1 minus uk, which basically is this guy q plus a minus s. That's what I have here. And then I apply expectation on both sides. Then I get a relation like this. And then in steady state, this expectation is same as qk. So I can just simply drop this plus 1. Then I have this equation. By the way, again, to do this, I have to first show that this expectation is finite. Then, so this is the same relation from the previous slide. I copy pasted here. Now the arrivals and service don't depend on the queue length. The service is potential service. It doesn't depend on the queue length. The unused service, of course, depends on the queue length. So a minus s is independent of q. So I can write this product of exponentials. I can write it as product of expectations, and then I can take this first term onto the left hand side. Then essentially, after simple manipulation, I get an equation that looks like this. So basically, this 1 minus e power u term is sitting here. This term was sent onto the left hand side. I pulled out e power q as a common term and sent the remaining to the denominator. Now, if I want to find the limiting behavior of this guy as epsilon goes to 0, all I have to do is take epsilon goes to 0 on the right hand side. But if epsilon goes to 0, this whole thing becomes 1. So 1 minus 1 is 0. Denominator is also 0. So I get 0 by 0 form. So what we do is we do Taylor series. So in the numerator, I expand this in Taylor series, but I only go up to the linear term. In the denominator, I go all the way up to the second order term. And that turns out to be the right thing. And it's not too hard to show that expectation of u is epsilon. Expectation of a minus s is lambda minus mu. That is also epsilon. Then essentially, and the second moment can be written in terms of the variance and mean square. Now I can cancel this theta epsilon squared terms and then take the limit. Then essentially I get something that looks like this. 1 over 1 minus theta times the average of variance. So all I did here, so you can ignore the algebra, all I did is this is the most important observation. And then once I have this u result, set the drift of exponential function to 0 and do the math. Then you get this. And this is the moment generating function of an exponential random variable with mean, this guy, the average of variances. Therefore, this shows I have shown that epsilon q, mgf of epsilon q converges to mgf of exponentials. And so this implies convergence in distribution. So I mentioned about the exponential test function. So essentially, we have convergence in distribution. We show that epsilon q converges in distribution to an exponential random variable with the same mean that we identified before. So the key idea here is that first, establish positive recurrence, which we did using Foster-Lyapunov theorem. Then set drift of an exponential function to 0 under stationarity. And then after taking the limits and simple manipulation, we get the limiting behavior. So there are three kinds of exponential function we can work with. The first one is what I showed. The understanding was that theta is a real number. In particular, theta should be should come from an open interval around origin. This can be thought of as two-sided Laplace transform of the stationary distribution, and this is the moment generating function. And to use this, one has to first show that this expectation, this MGF exists, because MGF may not exist for some random variables. The second kind of exponential function we can use is complex exponential. Instead of theta, we can use j omega. Omega is a real number. J is square root of -1. This can be thought of as Fourier transform of the distribution of Q, and this always exists, and this is the characteristic function of epsilon Q. So since this always exists, we don't have to worry about showing the existence of this guy, but this involves working with complex numbers. And the third thing, third option is I work with something that looks like the first option, but I'll let theta be only less than or equal to 0. I don't allow for positive thetas. And this always exists because my Q is non-negative. And so here, this is also very nice because I don't have to worry about showing the existence. And this is related to what is called as BAR approach in the literature. Okay. So that's all I wanted to say about using queues. Using stochastic recursions and Lyapunov arguments in a single server queue. So the key takeaway so far is using Foster-Lyapunov theorem to show positive recurrence, setting drift to 0 to get heavy traffic behavior. And then we can use two kinds of Lyapunov functions. Quadratic Lyapunov functions give mean bounds, or exponential Lyapunov functions give the whole distribution. And handling unused service is very important. And then I showed you two relations that we use for each of the Lyapunov functions to handle the unused service. And heavy traffic theory can be thought of as a generalization of basically this Q times U equal to 0. So if you recall, when I talked about the overview of various Lyapunov arguments we are going to discuss, I mentioned three. We already used the first two. Foster-Lyapunov theorem was the first one. Setting drift of a function to 0 was the second one. The third one is the global exponential stability. And then I'll show how to use that in the next part on stochastic approximation. So recall stochastic approximation. We're trying to solve a fixed point equation of this form. If I had h exactly, then I can simply keep applying it, and by Banach fixed point theorem, we'll converge geometrically fast. And but now we have a noisy oracle, so we are doing stochastic approximation of this form. And I said the noise is IID or martingale difference, which means it's mean 0, and the variance is bounded. In some literature, they assume variance is bounded by a constant, but we keep it slightly more general and we assume variance is bounded by b times 1 plus x squared. So the oracle is adding noise. I give it an x, it gives me h of x plus noise. The noise it adds could depend on my x, and the variance could also depend on x. And I'm assuming that the variance is bounded by this quadratic form on x. And it turns out that this general assumption on the variance is required to use stochastic approximation in the context of reinforcement learning. OK, so I mentioned about contraction operator, and then I introduced a norm, and then I said we are in Rn, but I didn't quite say there are many norms in Rn. And turns out we need to discuss about which norm we are talking about. And broadly speaking, the norms in Rn can be divided into two classes. The first one is norms that are defined by an inner product. There's an inner product, and the norm is basically x inner product with x. The standard Euclidean norm is of this form. You can write it simply as x transpose x, and this is the standard Euclidean inner product as well. Another example is we can use a weighted inner product. For example, suppose for any symmetric and positive definite matrix A, I can define an inner product. I can define a norm depending on A in this form. Norm square is x transpose Ax. And this is basically, it comes from an inner product, which is inner product between x and y is x transpose Ay. And turns out that if you have an arbitrary norm that's induced by an inner product on Rn, one can show that it can always return in this form. For any inner product in Rn, there exists a symmetric positive definite matrix A such that the inner product xy is essentially x transpose Ay. So working with a norm of the form in example 2 essentially covers all possible inner product norms. And when you have inner product norm, you can use all the properties that you're familiar with the Euclidean norm. For example, there is binomial theorem. X plus y square, norm of x plus y square is norm of x square plus norm of y square plus inner product of x comma y. There is Cauchy-Schwarz inequality. In contrast, there are other norms which don't have a corresponding inner product. For example, any LP norm where p is not equal to 2. P equal to 2 is the Euclidean norm. So LP norm with p not equal to 2 has no inner product corresponding to it. L infinity norm in particular, the soup norm, has no inner product corresponding to it. And then when there is no inner product, there is no binomial theorem. We'll see that binomial theorem plays a very important role in what we're going to do in the stochastic approximation for inner product norms. And that's the reason I'm highlighting this here. So in this part, I'm going to look at stochastic approximation when H is a contraction with respect to some inner product norm. So H is an operator we are interested in. It has certain properties. Maybe it's a contraction with respect to 2 norm, but not infinity norm. Or maybe it's a contraction with respect to infinity norm and not 2 norm. It depends on where this H comes from. And if H is a contraction with respect to an inner product norm, you can use the results I'm going to present in the next few slides. If not, you have to wait till part 2, and Zaiwei is going to talk about how to generalize these results when H is a contraction with respect to an arbitrary norm. And remember, I talked about 3 examples for stochastic approximation. The first one was from reinforcement learning. Some reinforcement learning algorithms correspond to this inner product norm. For example, TD learning fits into this framework, but Q learning does not fit into this framework. Linear stochastic approximation can be thought of as, again, fitting into this framework. The corresponding operator is contraction with respect to an inner product norm. And finally, optimization, SGD, fits into this. In fact, the inner product norm there is the regular Euclidean norm, the unweighted Euclidean norm. Okay, good. So let me now state the results. The first one is this is a stochastic approximation, but I'm assuming that the step size is fixed. It's constant. It's not depending on time k. In the next slide, I'll present the case when alpha k, the step size depends on k. And H is a contraction with respect to an inner product norm, weighted L2 norm, and the contraction factor is beta. So if the step size should be picked carefully, it should be small enough. I'm not saying exactly how small enough, but there's a bound in terms of beta and so on. Then if you look at the mean square error, firstly, there's a unique fixed point x star, and then I'm at xk after time k. I want to understand how far away I'm relative to x star. So this can be bounded by xk minus x star square. So then this mean square error can be bounded as follows. It has 2 terms. So this is a finite sample bound because there's nothing going to infinity. K is not going to infinity. This is true for all k. And there are 2 terms. The first term is a good term. It's going geometrically to 0. It is 1 minus something, and then this is power k. So this is going very fast. But the second term is a bad term. There's no k here. It's a constant. So what this is saying is that my x star is somewhere here. I start somewhere in the space. Then very quickly, geometrically fast, I approach x star. But after some point, so to speak, I'm not making any more progress. I'm as it were in a ball. This is what is captured by these 2 terms. So the first term is similar to the geometric convergence, the geometric ergodicity, geometric exponential stability of the ODE. And the second term is a constant. This comes due to noise and because we are using a constant step size. So the C1, C2, C3, we have closed form expressions for this in our papers. I'm hiding a lot of details so that we can understand the structure. But the C1 has the initial condition x0 minus x star, the initial error in it. And the C2 depends on the contraction factor. In particular, it is simply 1 minus beta. In general, for these kind of results, we like to call the first term as the bias and the second term as the variance. The second term is because of the variance in the noise. It depends on the noise variance, and it doesn't die as k goes to infinity. The first term is because of the bias in the sense that this term exists because I did not start at x star. If I started at x star and ran this recursion, the first one would not have been there. So it's a bias due to initialization. OK, now is that the ball is proportional to the step size alpha. This already suggests a way. So this is all good. Geometric convergence is good, but this is not satisfactory because I'm not quite converging to x star. Then this suggests a heuristic, which is that start with some constant step size alpha. Wait till you enter the ball. Once you enter the ball, you know you're not making any progress. Then decrease your alpha by half. Then you'll again geometrically go to a half-sized ball, and then keep doing this. So this is a heuristic that's used in practice, but a challenge in implementing this heuristic is you need to figure out when you enter the ball. OK, that's fairly simple. Look at xk minus x star and see whether you're making progress or not. Well, that's easier said than done because we don't know what x star is. So finding when we enter the ball is not as trivial as it sounds. So instead, what we'll do is we'll simply keep diminishing the step size alpha without worrying about whether I'm in the ball or not. In particular, I look at general step size of this form, some constant divided by k power psi, and this psi should be between 0 and 1. If it is 0, we have constant step size. We'll also look at case when it is 1. But if it is greater than 1, one can show that the stochastic approximation will not work. Okay, so suppose the psi is strictly between 0 and 1. Think of it as half, for example. Then the mean square error decays as 1 over k power psi, like 1 over square root of k, for example, when psi is half. Again, we'll have two terms, bias and variance terms, but I'm only showing the dominant term, the slowest term. And what this suggests is that if psi is large, then this has faster convergence. So which means that it's a good idea to make psi as large as possible. But this is an open interval 1. Then the question is, can I make psi equal to 1? What happens? So remember, there is a constant alpha here in the numerator. And when I showed this first case, this alpha did not show up. Of course, it is inside C4, but it doesn't affect the rate. But when you are looking at 1 over k step size, when psi equal to 1, this alpha plays a very, very important role. There's a threshold C2, is the same C2 from the previous slide, 1 minus beta. There's a threshold C2. If alpha is smaller than 1 over C2, then your rate depends on alpha C2. If alpha C2 is half, for example, your rate is log k over square root of k. But if alpha C2 is greater than 1, then you get 1 over k. Sorry, there is no log k here. This is just simply 1 over k. There's only log k here. Log k is only in the middle case. There's no log k in the last case. Okay, so 1 over k step size gives you the best possible rate of 1 over k. But the thing is, you should pick the C2, you should pick the alphas carefully. It should be larger than a threshold. If you end up picking it below the threshold, you'll end up sacrificing the rate. So if you don't know what this threshold is in a given problem, then simply pick psi to be like 0.99 or something like that. But if you are sure that your alpha is above the threshold, then you can go ahead and use 1 over k step size and then get 1 over k rate. And again, these constants have the initial error in them. And the C2, as I mentioned, is 1 minus beta. And finally, these constants also have 1 minus beta in them, the contraction factor. And in particular, it depends as 1 over 1 minus beta square in this case. OK, good. In the next few slides, I'll convey the intuition of the proof. So remember, I said how we'll always like thinking about ODEs, even though we'll not use it in the proof. So let's look at this is the stochastic approximation I presented in the previous slide. And the corresponding ODE looks like this. Send xk onto the left, alpha k onto the left, and then pretend this is a ODE, drop all noise. Then the first question is, does this ODE converge? And if we use x square as a Lyapunov function, norm x square, and then one can show that the ODE satisfies this inequality. The derivative of v is less than or equal to some minus constant, negative constant times v. And this essentially fits into our global exponential stability, the third of the 3 Lyapunov functions we talked about. And this implies that xt minus x star square converges to 0 exponentially fast. Essentially, this is saying that the ODE is very good. It converges to x star exponentially fast. So that's good to know. But like I said, we are interested in the stochastic approximation. And in particular, from the previous slide, we saw the best possible rate of convergence was 1 over k. And that is that's not a limitation of our proof. It's a fundamental limit. And that arises essentially for the same reason, because of 1 over k rate of convergence in law of large numbers. The mean square error in law of large numbers decays as 1 over k. So because of presence of noise, you can't kill noise faster than that. But the ODE has exponential rate of convergence. So the question is, how do we study the stochastic recursion, and how is this 1 over k rate going to show up? So to do this, let's actually look at the stochastic recursion, or this one. This is same as this. I just sent xk onto the left side. Ignore the bar. There's no bar here. And then if I compare this to the ODE, firstly, on the left hand side, instead of having a derivative, I have finite difference. So this is a discretization error relative to the ODE. Then this h of x minus x is same as h of x minus x here. This is the ODE term. That's a good term. I know how to handle that. And finally, I have noise term here. ODE does not have noise term. So there is an additive noise term. So basically, relative to the ODE, the stochastic approximation has 1, a discretization error, 2, an additive noise error. And we need to somehow handle these to get finite sample bounds for the stochastic approximation. And we have a step size here. And the step size is actually going to help us, because we can control these errors by playing around with the step size. So pictorially, my ODE, I have a Lyapunov function. My ODE is basically going down along this Lyapunov function. That's what it means to say that v dot is less than or equal to minus v. But my stochastic approximation is trying to follow it, but because of the discretization and noise errors, it's not quite following it. It's kind of doing a random walk around it. The question is it okay? Does this work? In spite of not following the ODE exactly, is it okay? And that actually, it depends. Since we are working with a inner product norm, a weighted 2 norm, it turns out that it is okay. Why? Because we have binomial theorem. And in binomial theorem, if you look at x square minus y square, you have something like a linear term, x minus y term, and a y square term. So the linear term is similar to the ODE term. And then the other error term, the second order term, can be controlled. So essentially, if we use the same Lyapunov function as from the ODE, that is the weighted norm square with an expectation, one can show a recursion of this form. The drift of this Lyapunov function, the difference of this Lyapunov function over 2 time slots, is bounded by a negative term proportional to v plus a little o of alpha k term. So compare this to the ODE. So in the ODE, I had dv by dt. Instead of that, I have a finite difference here. On the right hand side for the ODE, I had minus v. Here I have minus v, but then there is a term that depends on the step size alpha k. And there is a higher order term, which is little of alpha k. In particular, the little of alpha k is going to be alpha k square. So a key thing to be able to show this recursion. So essentially, this is the discrete version of this ODE. And the ODE basically looks at the linear approximation of the stochastic. If you look at the linear approximation of the Lyapunov function, that corresponds to the ODE. But the second order terms can be handled using binomial theorem for inner product now. So basically, binomial theorem enables us to control the discretization and stochastic errors, which are all hidden in the second order little o of alpha term. And essentially solving this recursion, we get the theorem, all the cases, the constant step size, diminishing step size that I showed before. So if I did not have this little o term, this is like geometric convergence. We could have had geometric convergence, but because of noise and discretization, this little o term is kind of inevitable, and that leads to a poorer rate. In the best case, it is 1 over k. So the key takeaways from the stochastic approximation part is that first look at the ODE. We don't need to analyze the ODE for the final proof, but studying the ODE will give us an idea of what Lyapunov function to use. And based on the ODE, we discovered that norm square is the right Lyapunov function. And for the ODE, this Lyapunov function enabled us to show global exponential stability. And so this is basically a quadratic Lyapunov function. Like in queuing, quadratic Lyapunov functions turn out to be good candidates in stochastic approximation too. But to use the same Lyapunov function for stochastic approximation, the inner product structure has been very important. In particular, we use binomial theorem in a crucial manner. Because I'm out of time, I can't show you the details of the proof, but the binomial theorem plays an important role to control the discretization and noise errors. So in the next part, when you go to general norms, we don't have binomial theorem anymore, and Zaive will talk about how to modify the Lyapunov function to handle the challenge. So this is the last slide in part 1. So to summarize, the main takeaway from this part and from the whole tutorial actually is that drift arguments are very simple, but extremely powerful. One doesn't have to work with heavyweight machinery like process level convergence, ODEs and SDEs, but finding the right Lyapunov function is the key. So far, I only presented very, very simple examples, and here simple quadratic or exponential Lyapunov functions work. The 3 kinds of Lyapunov arguments that we talked about. The first one is drift is negative. That's used to show stability. Second one is bound the drift in this form minus f plus g. Then by setting drift to 0 in steady state, you can bound expectation of f. And the third one is if you can bound the drift by negative v itself, then you'll get geometric convergence. But in the noisy case, the geometric thing is modulated and you end up getting a 1 over k convergence. So let's actually, before I close this part, let's compare the two parts, compare the two examples on queues and stochastic approximation that we discussed so far. Firstly, in queues, our whole focus was on steady state. Even when we talked about heavy traffic, that was still steady state analysis. First, we talked about existence of steady state, then we talked about bounding queue lengths in heavy traffic and steady state. In contrast, the stochastic approximation result is completely intransient in finite time. So these two show that Lyapunov arguments can be used to study steady state as well as transient. Then the Lyapunov functions we used were quadratic in both examples. And in queuing, we also worked with exponential Lyapunov functions. Quadratic gave us mean bounds, exponential gave us the distribution. And in the stochastic approximation, using quadratic Lyapunov functions gave us mean square bounds. And the key idea in queuing was to handle the unused service term. Basically, the qk plus 1 times uk equal to 0, that equation played a very important role that captured all the underlying inherent complexity of queuing. And for stochastic approximation, the challenge was in handling discretization and noise errors. First, you should look at the ODE. Relative to the ODE, handling the discretization and noise errors is key. And then even though I didn't illustrate why, I told you that binomial theorem plays an important role, and inner product structure gave us this binomial theorem. In the next two parts, we're going to look at various generalizations. In queuing context, we are going to look at multiple queues. Then the generalization of this equation qk plus 1 times uk equal to 0 is not going to be straightforward. And to study that generalization, we're going to introduce the notion of state space collapse, and we'll work with projections. So we have to modify the quadratic Lyapunov function, and we'll modify it using projections. This will be detailed in part 3. And in stochastic approximation, we want to study more general norms, especially the L infinity norm. It doesn't have a binomial theorem. Instead of binomial theorem, smoothness is going to play its role, but L infinity norm square is actually not going to be smooth either. Then we have to smooth it out, and something called Moro smoothing is going to play an important role. And that's how we construct Lyapunov functions in part 2. So even though the Lyapunov functions in this part were very simple, to actually get non-trivial results using them, to get results in more complicated settings, we need to modify these Lyapunov functions in some manner, either using projections or using Moro smoothing. And finally, by doing this, by modifying these Lyapunov functions, we were able to solve long-standing problems in both these disciplines. In the context of queuing, we solved a long-standing open problem on heavy traffic behavior in a switch. I'm going to explain all of it in part 3. And in the context of stochastic approximation for L infinity norm has been fairly challenging for a long time. And by Moro smoothing, we were able to understand that. And that immediately gave us a lot of results in the context of reinforcement learning. So the last 2 rows of this table are yet to come in the remaining 2 parts. So with that, I'll stop here, and thanks for your attention. And I'm happy to answer any questions.